the value of f prime of x. Now, if you didn't watch the video yesterday, then you don't know what f prime is. But if you did, what is f prime referring to? The function of the derivative. So whenever you see f with a little apostrophe thing, that's called prime. F prime refers to the derivative. So the value of the derivative equals the slope. TJ, put the pen down, please. Equals the slope of the tangent line. Feet down too, please. At particular values in f of x. So it's kind of wordy, but we're basically saying the derivative is the slope of the tangent line at specific points. So to sketch the graph, this is what we're going to do. We're going to start with the easiest tangent lines possible. What are the easiest tangent lines that we can draw in? The not changing ones, which would occur where? Maxes and mins, okay? So we are going to pick where horizontal tangent lines are, and we just identify those as the max min points in f of x. I want you to go ahead and sketch those in. So we have 3 of them. Now, remember the derivative is the slope of the tangent line. If the tangent line at these 3 points is a horizontal line, what's the slope of a horizontal line? 0. So if we were plotting the derivative graph, then at -3, the value of the derivative would be 0. So you mark a point. At 1, the value of the derivative would be 0 again. And then at 5, 0 again. Okay, so you start with the easiest tangent lines to graph, which would be the horizontal ones. Okay, so at those points, the value of the derivative is 0. Now, I know there's going to be a lot of writing with this one, but that's because I'm trying to get on paper what the thought process would be, so when you have to do this on your own, you kind of know how to think through it. You don't have to write out all of this every time you graph a derivative graph. Okay, so the value of the derivative is 0. We said x equals -3, 1, and 5. Okay, the next part that we usually focus on is we're going to look at where the slope, TJ, I'm not going to ask again, where the slope of the graph is positive. Okay, so we're looking at the original graph. Where is the slope of the graph positive?
From -4 to 1.
Close.
From -3 to 1.
-3 to 1, and that's where my function is increasing, right?
And then 5.
So we would say the slope of the graph is positive. If I was to draw in a tangent line there, it would be a positive slope. So that occurs where the graph is increasing. Okay, this happens between, we said x equals -3 and 1, and then again where? Happens one other place.
5. Yeah.
Between 5 and 6. And then again at x equals 5 and 6. Okay. Here the graph of the derivative be positive. Now, why is the graph of the derivative positive? Because it's a positive slope, and derivative is the slope of the tangent line. Okay, and so we're going to actually, to figure out what to graph, we're going to estimate the values of the slopes at each x to draw in the points for the derivative. Well, yeah, this is just evaluating in case you don't have, because sometimes, like with free response problems, sometimes they have the original graph and you have to evaluate the derivative and you're not given the derivative function. Or maybe you're only given a graph, you're not given a function at all. Okay, so we're going to start with -2. We have the value of the derivative for -3. We're going to focus on the next piece here. Just go ahead and draw in, as best you can, a tangent line. We're going to estimate that slope. Now, this is going to be a rough sketch, but you'll see a pattern start to emerge, and then you can kind of go with that pattern instead of having to calculate each one separately. What is the slope of this point here? Does it look like? Or sorry, this line. If you started here, 1, 2, 3 over 2, I think that's a pretty good estimate. So 3/2 is what decimal? 1.5. So we're going to go ahead and plot that. So at -2, plot a value at 1.5. So we're saying, okay, in my original function, the slope of the graph at that point is 1.5. Oops. That should not be there. I smudged my pen. So it looks like a line, but really it should just be a dot here and a dot here. All right. And then we're going to go to the next value, which is -1. Go ahead and sketch. Is it going to be a little bit steeper? Okay, so then following that pattern, maybe it's at a 2. Can we say it's a slope of 2? If it's a little bit steeper than 1.5. So then I'm going to mark at 2. And then at 0, is that going to be steeper? It's going to be a little shallower. So is it going to be as steep as 1.5, or is it even shallower than that? Is it at 1.5? 1 over 1. So maybe we say that's at 1. Do you see here that if we were to connect these dots, you're going to have somewhat of a curve there? Okay, so we have a pattern starting to emerge here. Because what does this look like? That kind of looks like a sinusoid. Okay. That'll come back later. Alright then, and 5 and 6, we can assume that that's maybe 1.5 again. Below be the complete opposite? Yeah. Okay, so then, after you take care of the positive parts of your graph, what's the next thing that you would look at? The negative. So you're going to look at where the slope of the graph is decreasing. So where the slope of the graph is negative, this would be where the graph is decreasing. And where does this happen? Between 1 and 5? And between -4 and -3. Okay, and then you evaluate or plot points again by drawing in estimations of tangent lines. So notice my graph's getting a little messy here.
What if your estimation
start graphing points, if you notice, well, some of my points are a little off, but I can start to see that it might look like a sine curve. Then you just kind of know what the pattern is supposed to look like and then go with it. So we can kind of see here, since we know this is going to drop down below because it's decreasing here, at 2, wouldn't this be the same slope, just negative, of this line here that I drew in? Yeah, so we had that at 1, right? And then if I was to draw in a tangent line at 3, that's a little steeper, so maybe I'm at -2 there. That's the slope of -2. And then at 4, is that as steep or a little less steep? A little less steep. So maybe we're at 1.5 again, or even 1. But you should see this pattern start to emerge. Now, over here, you can draw on the tangent line, but you can kind of assume it's going to be following the same... Oh, man, that pen isn't good to use for notes. Sorry. You can kind of assume it's going to be the same pattern as it goes. Now, this kind of looks like a cosine function, right? Shifted a little bit, but it kind of looks like a cosine function. And this one kind of looks like a sine function. Eventually, we'll start to get to taking derivatives of sines and cosines, and they are actually each other's derivatives. Derivative of sine is cosine. Derivative of cosine is actually negative sine, but... Hmm?
Something scary.
Yeah.
Really?
Not scary, scary.
You lied to me when I asked you if there was a law of tangents. You didn't say law of tangents.
Oh. Alright, we are going to flip, and with the person to your right, and Addie, would you pair up with TJ maybe? With example 3, I want you to graph on your graphing calculator. I want you to find the numerical derivative. This is what we were doing yesterday.
Let's just pair up the two. Who's the person to my right? Yeah.
And then find
If he went all the way over here.
the high and low points and just make connections, because when you graph, do we need a little refresher on how to do this since some of us didn't watch the video? Oh, well, let's at least get the graph all together. Get your calculator.
Yeah, Miss Cross, I didn't have my property sheet trying to do the review, and so I just Googled like a property sheet, and there was a law of tangents.
Oh.
It was weird.
Oops, sorry. Everyone needs this in their calculator, and you better be following along because this is something that you're going to have to do on your own. Okay, so in your y equals, you are putting the function for example 3. TJ, you can be doing this too.
Watch me.
If you need it on your own too. And then for y sub 2, you're going to be graphing the numerical derivative. Which, can someone tell me what menu it's under?
Oh, that's under the, sorry, it was math.
You go to the math button.
Number 8.
Then you go down to where it says end deriv. Now, the numerical derivative, what the calculator can do with this, it cannot give you the derivative function. What it can do is it can calculate, much like what we did in example 2, it can calculate the derivative or the slope of the graph at every specific point by using like average rates of change. It does all of that for you and plots all those points. So you'll notice that when we graph numerical derivative, it graphs very slowly, but that's because the calculator is finding the estimations of the derivatives at every single x on your screen. So it's going to take a little bit. So you select end deriv. The input that you have to put in there is you need to put the function that you want, which we've already put into y sub 1. So you go to vars,
That's not all of mine.
y vars,
It yells at me for argument.
Wait.
Mine doesn't look like that. Yeah,
Mine
mine doesn't look
Mine
like
is
that. Like the
Ours like that.
mine looks
Mine looks the same to me.
So does mine. Mine
Yeah,
looks
but
like
it's
this.
a new one.
Ah.
No, mine
But then go to vars. Oh.
No,
Y
no, no.
vars.
If you go to vars and you have to go over to y vars.
Dang it.
this is what yours looks like?
Oh.
Yeah. Well, mine doesn't have the big
Well,
glare on it.
go in there. X.
Hmm?
Let me just see if this
See,
works.
that's why I give the simplicity.
What?
See, probably won't.
Good old does not mean that it works. More educated. Or have wisdom
I'm
to
just gonna
learn.
see if this works here. So
He yelled at me again for argument. And no, didn't yell at you. That's weird.
okay, so with your new calculator, if you have one of these newer calculators, hold on. You like when I did the video on the older ones, you have to put y1, x. In these ones, you put an x here, y1, and then you put an x over here. So it's just making the format look a little bit different, but you still put in all three inputs.
What's your window?
There we go.
I just did the standard window, but I'm gonna have to fix it a little bit.
So, Ms. Cross, how do you plug in the n derivative in the old version?
What?
You have to press you go y1 then comma x.
So then after the y1 you're gonna do yeah.
There, now it's working.
Okay, let me go and adjust the window a little bit.
I'm not throwing stuff. I'm just setting it on the table a little bit roughly.
I'm gonna zoom out a little bit. I'm not sure. Okay. The other thing that I'm gonna do here. Come on. I'm going to make this graph a little darker. I'm going to zoom out one more time by making it maybe go to negative. Sorry. Well, we'll keep that negative 20 to 20. I think this needs to be up a little bit. So we're going to go 50.
Function that just makes it so that your calculator just makes a window that perfectly fits your function?
Not perfectly every time, no.
Is there a
Zoom
function
fit
that will
sometimes does nicely.
What'd you do?
What is zoom fit?
Okay. I'll show you my window here in a second, but gentlemen. I'll show you my window here in a second, but your goal in this example with your partner is to look through the original graph, which is that cubic fixed graph, and then the darker piece that the calculator graph is the representation of the derivative, that you are making the connections and you're saying, okay, well, where my original has a minimum, what's happening with my derivative? Where my original crosses the y-axis, what's happening with my derivative? Where my function is increasing, what's happening with my derivative? So you're just looking back and forth between the two graphs and trying to make as many connections as possible on how they compare and contrast. Okay? My window for this one, to make it even better, you can probably go from negative 10 to 10 on the x.
Yeah.
And
And it
then
doesn't
from
split.
negative 20 to 50 on the
My window makes a lot
y.
more sense. And it's zoom fit.
Let's see. So where is negative 10
And that's what you're doing for the next 10 minutes or so.
plus
You will have an exit ticket, and this is where we'll start
plus
Yeah, we're doing the
at the beginning of class tomorrow.
Cross.
Yeah.
I need you to help me graph the derivative. No,
Who's
what
with
you're,
us? Is that your...
what your explanation was kind of where there's a
Zoom in.
we're not doing the corner stuff anymore. But if you wanted to do it to have it fit on
that right there is the derivative.
but we're doing like the hours portion. Cause with
we were gonna
with this one she gave us the function X
Languages and mathematics. Is that like K through 5 education? Or is that like some sort of bridge building company? How do you calculate stress? I don't know. Oh wait, she's still recording.
I guess you just get to sound like a tard on the internet.
Thank you for calling me stupid.
I said tard, actually.
That means stupid.
No, it means tartar sauce. Actually, it means tartar sauce. Like,
Oh yeah, of course,
don't be a tard. No one wants to dip fish sticks in your brain.
I'm gonna turn off the microphone now.